All right, so for iOS development, we're going to be using Swift, which you can use Objective-C or Swift for iOS development. We'll be using Swift in this class. And so we're going to do an introduction to Swift where we learn about a lot of the stuff that you will need in order to be able to write iOS apps with Swift. So when I'm learning a new programming language, I tend to have a set of questions that I go through in order to understand the basics of that language as quickly as possible. And I had to develop this while I was working as a consultant, where we were expected to be able to learn a new programming language to like a consultant level of proficiency. And we would get, if we were lucky, we got 2.5 or 3 weeks to do that. And if we were unlucky, we got a couple of days. But it took, I would say, like between 80 and 100 hours to get from like not knowing anything to be sort of consultant level fluent. And we were able to do it in that kind of compressed amount of time because we were able to isolate the things that were most important to understand in this language and start with those. So I'm going to introduce you to those questions here. And the other thing that we're going to do is we're going to compare Swift as a programming language that's new to us to a programming language that we know. Because one way to go through this is to try to memorize everything about Swift, but a more effective way, in my experience, is to take something that I already understand and compare it to Swift so that the Swift knowledge is linked to this previous knowledge that I already have. Since the entire class has done Python before, we are going to do this with Python. Let me start my video here so that you can see me. Okay, so these are the questions that we're going to go through, and we'll just take these one by one. So we'll start with the type system in a programming language. So the question is whether the language is statically or dynamically typed. Now, in Python, we use dynamic typing, meaning that we don't have to declare what a specific type is for an argument when we define a method or when we declare a variable. And then at runtime, Python interprets based on the type that has been passed in. This is also referred to as duck typing, and Ruby does this as well. Now, Swift is not like this. So Swift is statically typed, which means that we need to declare the type, and the type is assumed, and it stays that same type. The variable stays that same type. The argument stays that same type, what have you, for the duration of the life of the code. So you can see an example of this here. We have this variable called 30. We declare its type to be an int, and then we declare its value to be 30. So Swift has a number of primitives that we can use. They include int, double, string, and bool. So in Swift, we don't say integer and boolean. We say int and bool. And we can declare types like this. So for example, if I wanted to declare this type to be a boolean, I could make this boolean, and then I could set it to one of the values for a boolean, which in this case would be true. Now, the tricky thing about Swift is that it is statically typed, but it can look dynamically typed in certain circumstances. So if you look at lines 7 and 8 here, you can see that 10 and 20 are declared without a specific type. They are in fact statically typed, but Swift uses something called type inference in order to be able to determine what type something is based on its initial value. So if we are giving an initial value to a type, then Swift will use that to determine what that type should be. And you can't reassign it. So I'll give you an example. If we wanted to reassign 10 at this point to a string of 10, and I try to run this code, I'm going to get an error. Cannot assign value of type string to int. Reason being, the type has been inferred up here to be an int, and we can't change it after the fact. So Swift statically typed, but has type inference, so can sometimes look dynamically typed. On lines 12 and 13, you can also see strings. They work exactly the same way. Just like primitive types in Python, primitive types in Swift can have methods that you can use on them. So for example, when I add the integers 10 and 20 here on line 10, That's going to give me 30. Whereas, what is it? Sometimes it takes, yeah, there we go. All right. Whereas if we add 40 and 50 on lines 12 and 13, we get string concatenation. So this is relatively similar to the behavior of the plus operator in Python, where we add things together. All right. So that's our first principle, static or dynamically typed. Then I want to know a little bit more about the types as well. So we talked about the basic types in Swift for representing strings, numbers, true, false values. We also want to talk a little bit about what types are available for representing collections. So in Python, we have a couple types available to us for representing collections. We have a list, which we can declare like this, and then that list object is available to us. We also have what Python calls dictionaries, and dictionaries are similar to lists except that the index can be anything, and I'll explain what I mean by that in a second. But I can make a dictionary, and that'll look something like this. And let's say 2, 2, like that. So now I have my dict available to me. Good. All right. So there is one thing before I move on that I want to talk about with respect to lists and dictionaries, because folks kind of see these as completely separate data types sometimes, and I want to emphasize the similarity between them. What a list is, or what some languages will call this an array, is it's a collection of items that you can access with an integer. So if I say list 0, then I'm going to get the first item in the list, which in this case is 1. So I can get the 1, which has an index of 0. A list is indexed with integers. A dictionary is exactly the same in its API, with the exception of the fact that you don't have to use integers as the indices. You can use anything as the index. It is like a list, except that the keys can be any type rather than just an integer. So, for example, for a dictionary, we get the first value by using this key of 1. We could also make a dictionary, though, that has integers as keys and then operate essentially like a list, where we would be doing that. So that's lists and dictionaries in Python. What about in Swift? Well, in Swift, we also have arrays and dictionaries. Here on line 21, you can see an example of an array in Swift. So this is an array of strings. I've called this array books, and I've included some initial values of strings of titles of books that I have here in my office. The one device, crafting interpreters, one small step. So in Swift, Swift wants all of the types of all of the objects in an array to be the same. So we couldn't, it wouldn't like it if we put that. We get an error. Heterogeneous, collection, literal could only be referred to any. Add an explicit type annotation if this is intentional. So what it's telling me is that if I want to have multiple different types in this list, I have to explicitly say this list is a list that contains types of the superclass of all of the types in Swift, any. We'll come back to casting later as we start building our iOS apps. But the point is that Swift does not like us implicitly attempting to include different types in the same collection. So just like the integers or the strings, collections have methods on them that we can call. They're a little bit different from the methods in Python. So for example, in Python, if we want to get the length of a list, we use a data model method like this. It's called len, and we pass the list into it as an argument. That gives us a length of 3. So in Swift, rather, we're getting the length of our list with count, and we call it on the array object itself rather than passing it in as far as the API is concerned. So this is an array in Swift. When we loop through arrays in Swift, we have a couple of options. There's an approach that you may have seen if you've written Java, particularly before the for in syntax became popular in Java, which is to index through an array for some I. As you increment through up to the length of the array, you do stuff with the array indexed in I. We can do a very similar thing in Swift, which is demonstrated here on line 29. Execution was... Here, let's rerun the whole thing. Oh, because the index is too high, because we are calling on a list of 3 things, and it thinks we're calling on a list of 4. There we go. So that kind of error is what you'll get if you're using explicit indices and you miscalculate what the index is or mess something up like that. So we don't generally use this approach. Instead, in Swift, we use what's called for in syntax. And so you see that here on line 33, where we can say for some individual item in our collection, we print that specific item. So we do this in Python as well. We have that for in syntax in Python as well. All right. So then we have dictionaries, and just like Python, they're called dictionaries in Swift. Some languages call these hashes, some languages call these maps, but in this case, it is a dictionary. So a dictionary, like we said, is an array where the keys are an arbitrary type rather than specifically integers. So you can see an example here on line 39 of a dictionary effectively mimicking a list. So we have this dictionary, integer to string, with keys of 1 and 2, and values of strings representing 1 and 2. And we can access those values with the integer keys on line 40, just like we would do in a list. This is the equivalent of if we had an array called numbers, and we did this with it, with the exception of the fact that this array is going to be 0 indexed and this is 1 indexed right now. So it would be exactly the same if these 2 keys were 0 and 1. And then this would, cool. All right. Then on line 43, you can see an example of a dictionary where we use strings as keys. And so in this case, we have the string of 1, which we can access and get to our value of 1. In Swift, the values in a dictionary can be of any type, but it wants all of the keys to be of the same type. So it's going to want, if you're making a dictionary and one of the keys is a string, it's going to want all the keys to be a string. Whereas the values can be of any hashable type. They have to conform to a protocol that allows them to be hashed. But other than that, they can be anything. Okay, so these are your basic collection types. You also have access to a set in Swift. We have sets in Python too. We don't end up using them too much, so I'm not going to worry about them too much in this tutorial, but you do have access to that as well. Lists and dictionaries, though, will be the key collections that you're going to use most of the time when you're writing Swift. All right, so what's our next question? Conventions. So conventions refer to the way that we colloquially write a language, the way that programmers have agreed that the language should be written, maybe regardless of what's necessarily going to compile. So in Python, we have a set of conventions called PEP8, and you can run linters and stuff that'll make sure that your code is conforming to the PEP8 conventions. In Swift, we don't necessarily have that kind of coalescing going on around a sort of common understanding of what everything should look like, but we do have conventions with regard to what is Swifty code and what is code that maybe works but isn't necessarily particularly Swifty. The word we use in Python for this is Pythonic. So here's an example. Let's talk about capitalization conventions. Now in Python, generally our variables are going to be snake-cased, which means that if we have a variable with multiple words, let's say here's a variable, we put underscores in between the words and everything is lowercase. Then in the case of a constant, we might do this is a constant. And we might indicate that with uppercase letters. The compiler, or the interpreter rather, doesn't interpret these two variables differently. However, we use the convention of capitalization to indicate what's supposed to change and what's not supposed to change. We'll talk more about mutability a little later. Now, in Swift, we don't use snake case. Instead, in Swift, the variables are camelCased, which means that when you have a variable with multiple words, like you see on line 48, an integer to string, we capitalize the first letter of the second, third, fourth word, and so on. Now, what you see here on line 48 is called small camelCase, which is what we use for variables and method names in Swift. Small camelCase means that the first letter of the first word is not capitalized. Compare that to where we make a class. We'll come back to classes a little bit later, but here on line 78, you see an example of a class declaration in Swift. Here, nonfiction is capitalized. This is big camelCase, and we use big camelCase for classes and enums in Swift, as opposed to the variables and the methods. So that's the convention in Swift. Let's also talk about conventions with respect to conditional logic in Swift. So in some languages, like Kotlin and a bygone Java, when you have a conditional like we have here on line 57, you need to put parentheses around the condition. You're going to see this in Kotlin later when we write Kotlin. This is going to work in Swift. That having been said, we don't have to do that, and the convention is not to do that. So we write, typically, our conditions like this. Now in Python, it's the same thing. So in Python, we can put our condition, and we don't have to put parentheses. Okay, so this should be capitalized, but the point is that we don't use parentheses in Python. Okay, so that's some conventions. You'll get introduced to some of the other conventions as we kind of write more Swift in this class. So the next question is around mutability. How does this language determine which variables are mutable? This is a case where Python and Swift differ quite a bit, and it has to do with the original philosophies of what each language is like kind of for. So in Python, sort of the idea is to keep the language as flexible as possible. Performance is a secondary concern to the legibility and the flexibility of Python. That absolutely has its place, and we've seen that borne out in the fact that Python is used for everything from web development to machine learning models to you name it. So that's valuable. In Swift, we're dealing with a very specific set of constraints, though, which is that Swift is chiefly for iOS apps right now, and the iOS operating system has to operate on a very small computer. So it's really important that as much space be saved as possible. And for that reason, we see a couple of differences in the way these two languages handle mutability. Mutability refers to variables that can change. And when you make a language mutable, you add a whole bunch more complexity relative to a language where everything just stays the same immediately after you declare it. Let me show you how Python does it, and then I'll show you how Swift does it. So in Python, specific types are mutable or immutable. So for example, we have, let's say we have a variable called, whoops. Let's say we have a variable called 1 in Python. Let's look at the ID of that 1 variable. Okay, so if I reassign this variable, it's still attached to the name 1, but effectively, this is a different ID. Python has created me a completely new variable to hang on to this value. And 1 is now pointing to a completely different place that has the 2 stored in it rather than the 1. This is the way the primitive types work in Python. So your Booleans, your strings, your integers work like this in Python. In the meantime, your collection types and your user-defined types, so if you were to make a class, that's mutable in Python. List is mutable in Python. Dictionary is mutable in Python. So if I were to add an item to my list and call it 4, like this, list assignment index out of range, what am I doing? Let me change, what I want to do is change the last value from 3 to 4, 0, 1, 2. 4, like that. Cool. So now when I look at list, it's 1, 2, 4, whereas it previously was 1, 2, 3. You know what I didn't do is I didn't show you the ID of list. So here's the ID now, and then if we change that back to 3, let's do, I move a little slow when I'm writing 2 programming languages at the same time. Okay, so these are the same ID because the list is mutable. List is still pointing to the same place, which individually points to each of the items in the list. So it's all done implicitly in Python. We didn't have to say, make this variable one that I can change, make this variable one that I can't change. As far as the Python API is concerned, everything looks changeable to you. Python relies very heavily on conventions rather than compiler enforcement for the mutability of variables. So compare that to Swift. Back up at the beginning, we declared a couple of variables here. We said var 10 equals 10 and let 20 equals 20. These keywords var and let are how we explicitly indicate which things are mutable in Swift. So we've seen already that we can redefine 10. Now let's try to redefine 20. So let's say 20. Let's reassign that to 21. So it says, cannot assign to value. 20 is a let constant. Change the let to a var to make it mutable. I'm not going to fix that now, but we use these let constants to indicate when something should not change. This assists the Swift compiler in determining how to store references to things for more efficiency. Whereas Swift would take up more space if it took the approach of just allowing everything to be mutable and allowing variables to hang around. So when we reassign 1 to 2, that other ID for the original 1 is still hanging around, and Python ultimately has to garbage collect that. We don't get that stuff hanging around as much in Swift. All right, so that's mutability. Let's also talk about the paradigm. So in a programming language, we might be able to write one of 2 styles. The first is imperative. You may have heard this referred to as object-oriented in the past. The 2 terms, imperative basically describes what a programming language should be able to do, and object-oriented is an implementation of an imperative approach that allows you to do those things. That's how those 2 terms differ from each other. So we have imperative, or we could have functional. Now, there are languages that are specifically devoted to functional programming. Haskell is specifically devoted to functional programming. We have languages that are specifically devoted sort of to object orientation. In Ruby, for example, everything is an object, although you have functional APIs available to you in Ruby. Now, Python has an orientation as well. Python has an object-oriented approach chiefly. So we use objects in Python. We're declaring things inside of objects, usually rather than passing functions around. However, in Python, you can take a functional approach. We do have functional methods in Python that you can use. So similar to Ruby, the underlying structure of the language is object-oriented, but it has functional APIs that you can use. Swift, by contrast, was designed kind of specifically to allow for an object-oriented approach or a functional approach. That makes it an effective teaching language for comparing the two approaches, which is really nice and is going to give us the opportunity in this class to see where one might be useful over the other and the circumstances in which one might be preferable. We're going to look more at objects in Swift in a little bit, but first I wanted to go ahead and show you here on line 69 what a functional approach to Swift might look like. So here we're using a functional method called map. And what map does is it takes this collection of 1, 2, and 3, and it performs an operation on each of those objects, and then it returns us a list with those objects with the operation performed. So in this case, the operation is to make the strings uppercased, and we see the result over here on the side. This $0 syntax in Swift is syntactic sugar that we use to refer to the item that we passed into the map function. So $0 refers in this case to 1, and then 2, and then 3. So we're going to look at the object-oriented approach next when we talk about collaboration. So the next question is around how the language deals with inheritance or interfaces. Now, in Python, we have inheritance. So we'll have a class, subclass from something else. So you might have your special version of a string that extends from string, or a special version of an object that extends from object. Typically in Django, we use inheritance a whole lot to extend from stuff that Django provides us in order to be able to make our web apps in Python. That having been said, in Python, we don't really use the concept of interfaces. Native Python doesn't really have interfaces. There are some libraries that attempt to help you do the same thing, but Python doesn't really ship with interfaces. An interface is different from a class, because while a class comes with functionality in it, an interface defines a contract of stuff that a class that implements it needs to be able to do. I'll show you what I mean with Swift, because Swift does have this concept. So first of all, in Swift, let's talk about what a class might look like. Here on line 74, you can see a very basic class in Swift. I called it book, and it has one attribute in it called author. That is a string. The type here you'll see has a question mark on the end. We're going to come back to why that's the case. So this is a class in Swift. We can subclass from book in Swift. So here on line 78, you see nonfiction, which is a subclass of book. It adds another attribute called subject, but in addition, it also has access to the author attribute from book that it inherits from. So here, in its initializer, which allows us to create a new instance of this class, we can have both the author and the subject passed in, and Swift understands that it has access to the author because it subclasses from a class that has the author. And then we can set both the author and the subject with our initializer, like you see on line 89. We create a nonfiction book called Object Design with an author of Rebecca Werfsbrock and a subject of programming. Okay, so now let's talk about interfaces. In Swift, we do not call this an interface. We call it a protocol. but it's similar to the interface concept that you'll see in most programming languages that have this. So for example, Java has this. We've called this protocol indexable, and what indexable does is it says anything that implements this protocol must have all of the methods that I define. So inside of indexable, we have a method signature. A method signature describes what the method is called, what gets passed into the method, and what's returned out of the method. So for example, here on line 95, we use the func keyword. That's Swift's equivalent of def in Python that we use to define functions. Then we have the name of the function, index. In here is where we would put any arguments that need to be passed into the function, but this one does not take any arguments. Then we have an arrow, and after the arrow comes the return value. So the return value in this case is a dictionary with strings as keys and integers as values. So anything that implements indexable has to have this method on it. Protocols are useful because when we want to be able to pass around objects from one place to another, sometimes we may want to be able to guarantee that that object has a specific functionality, but different objects might need to implement that functionality differently. The example that I like to use here is that you can imagine yourself as a student. When you graduate, you'll implement like the Master's in Computer Science interface. And what that tells potential employers is that you implement this interface, which means that you have abilities like make complex software decisions. So you have a method called make complex software decisions that you have implemented, and they are able to ask you to do that. Now, the specific implementation might be different. You might make those decisions differently than one of your classmates does. Your different instances, your different implementations, but you both have the ability to make those decisions. That's what a protocol is. Okay, so on line 98 here, we see a class that implements a protocol. Let me show you what happens when we implement a protocol. So you see here we have a class called reference. It inherits from nonfiction, which means that any functionality in the nonfiction class, the reference class also possesses. Now, I'm going to add a comma to indicate that I also want reference to implement the indexable protocol. We can add as many protocols as we want in Swift. We can only inherit from one superclass. We're single inheritance, but we can implement as many protocols as we want. So you'll notice that I have an error here. It says type reference does not conform to the protocol indexable. Do you want to add protocol stubs? This means that that the compiler has noticed that we want this class to implement indexable, but this class doesn't have the methods on it right now that indexable insists that it have. So we need to add that method. And the way that we can do that is by clicking this fix button, which adds a protocol stub. This puts the method in there for us with the required signature. So we have index the name, doesn't take any arguments, and then it returns our hash. In here where it says code, this is placeholder, and we would add our implementation in here. So for reference, we're going to return a default implementation right here of an empty dictionary, just to get things compiling. But here is where you would be able to implement whatever functionality you need to provide an index of topics to page numbers. So that's implementation of interfaces. And we can see here on line 105 that the initialization of our reference object is exactly the same as the initialization of our nonfiction object on line 89. All of the same functionality is there because reference inherits from nonfiction. Now, there is one more thing that Swift provides for us with respect to objects and inheritance. that I want to point out to you. Python doesn't have this. And in fact, most programming languages do not, is the extension keyword. When you make an extension like this, you are effectively adding functionality to the original class. So in this case, I've made an extension of reference with a method in it called level of confusing that rates how confusing the book is to read. The compiler would treat this exactly the same as if I took this out of here and put it in the original reference implementation there on line 104. So the reason that we might use an extension is to be able to organize the functionality of a class that has a lot of code in it that needs to implement a bunch of different interfaces, for example. So suppose that I have a class that implements like 8 different interfaces. I might make an extension to implement each of those interfaces. In the case of reference, maybe I would make an extension of reference that implements indexable like this. And then I could move this functionality down, and that would work exactly the same as if I had it up here on line 98, but I could maybe define attributes and stuff just like I did here. So I don't know. I could define new attributes in here or what have you. And then my indexable protocol doesn't need to be up here anymore. I stick all my attributes into the original reference definition. And then my indexable functionality is handled in this extension down here. Originally, when I started writing Swift, I thought that extensions seemed superfluous, but as I started writing more complex Swift, these became a really nice way to organize my code. So I want to point those out to you. All right, collaboration was a big one. We have one more big one, which is handling null. Languages have all kinds of approaches to handling null. So we want to know how each of our languages deals with null values and what we need to do to handle null values. Now, in Python, we can declare, we have this type called none. None is your null in Python. And if something is null in Python or something is none in Python, and you try to call a method on it, you're going to get an error. So let's say, so it says object of type none type has no length method. This is what's going to happen if something has not been assigned at the time that you're attempting to call a method on it in Python. So we'll tend to do null checks on something like that if it's possible that something might be null. So let's declare our one variable again. And suppose that we want to print out a value if it is present. We might do something like if one is not none, we'd print 1. Okay. So this right here, we refer to as a null check, and we see these in a lot of programming languages. So we'd see these in Java, for example, to avoid getting the famous NPE, null pointer exception. Swift attempts to get out in front of this problem, and I'll show you how. So you'll remember the question mark that we saw earlier on when we were looking at some code, and you'll see it again here on line 124. In Swift, we deal with nulls using what's called an optional. An optional, represented by this question mark, means it is possible for this value to be null, and therefore you must handle the possibility that it is null, or Swift will not compile. So there are a couple of different ways that we can do that. One way that we might try to use is the null checking that we saw previously. Let me show you what happens if we try to do that. with this code here on line 126. If favorite book is not nil, then we want to print it out. But what you'll see here is that I get an error when I try to run this code. It says, value of optional type string must be unwrapped to a value of type string. Here's why that's happening. We know, you and I know, based on line 126, that we only get into the body of this if favorite book is not nil. But at this point right here on line 127, the compiler doesn't know that favorite book is not nil. It only knows that favorite book is some variable of an optional type. So it offers us some ways to make sure that something is there at that time. One note here, since we're going to be writing Kotlin later on, is that Kotlin does recognize in this circumstance that favorite book is not nil within the scope of this code. So this is another difference to be aware of. All right, so what are our options for dealing with nil here? Well, the first one it mentions is coalescing. Nil coalescing is the fancy term we use in Swift to describe having a default value. So we can say fix here, and favorite book with a default value of some book. Okay, so in this case, if favorite book is nil, then what's going to be included in this string is some book, and we don't have to worry about whether or not favorite book is present with respect to the code compiling. Let's look at the other option. It gave us two options. So we did nil coalescing. Now it says force unwrap using an exclamation point to abort execution if the optional value contains nil. Let me show you this. Now, favorite book has an exclamation point. It is force unwrapped. When we force unwrap things in Swift, we're saying, listen, Swift, I know you're worried about the fact that this could be nil, but I know what I'm doing, and I promise you this variable will not be nil at this point. So we know on line 126 that favorite book isn't nil, and we can safely force unwrap it on line 127. If we are wrong about the value on line 127, and somehow we manage to force unwrap something that is in fact nil at the time that we try to force unwrap it, the app is going to crash. That's not necessarily the end all be all. It's not the absolute worst thing that could happen, but it's worth noting if we're using force unwrapping, we need to use it responsibly because we are promising our application that this thing's not going to be nil and the app's going to crash if we're wrong about that. Now, for that reason, we have another way to do this functionality so that we don't have to check for something to be nil and then force unwrap it. We have a more elegant solution available. It's called optional binding, and you can see it exemplified here on line 137. If let confirmed value equals favorite book. What this means is if favorite book is not nil, assign it to a variable called confirmed value with a scope of this block of code. So confirmed value, the variable, is destroyed after this code runs. But inside of this block of code, Swift knows the confirmed value is not an optional, it is definitely there. So here we can use confirmed value without force unwrapping it. If favorite book were nil when we got to this code, this whole conditional would be skipped. So this is the way that Swift attempts to elegantly deal with the handling of null values. And I should mention the word that we use for null in Swift is nil rather than none, which is what Python uses. All right, that was the last really big concept. We have a couple of other small concepts to cover. And these concepts might sound new, And we'll talk about why we're discussing them because they may seem like small things. We're going to talk about precedence and associativity. So what is precedence? In a programming language, precedence is the order that operations are run in if they happen together with different operators. So let me show you what I mean. If we do 30 divided by 10, or let's do 30 plus 10 divided by 20 plus 20 in Python, what is this going to produce for us? It depends on whether the addition operations are run first, if those take precedence, or the division operation runs first, if that one takes precedence. So in this case, we get 50.5. Why? Because 10 divided by 20 is run first. Division gets precedence. That gives us a half. So then we have 30 plus 1/2 plus 20, and we get 50.5. Let's see how that looks in Swift. So we run the same thing on line 141, and we see that we get 50. The reason we don't get 50.5 is that all of the variables on line 141 were initialized as integers, whole numbers. And so when Swift is dealing with integers divided by one another with a result of an integer, it truncates the result. So it gets 50.5 here, but the result is expected to be an integer because it's the addition of all these integers. So it truncates it down to 50. This seems like maybe a minor thing to be talking about, operator precedence, but it's really, really important if you're running into like an insidious bug where a couple of different operations are happening on the same line. So we have a number of operators in Python like and or. When you string these together, it's really important to understand which ones are getting operated on when, or else you're not going to necessarily end up with what you expect. So if we do true and false or true, true and false or true, we get true here. Why do we get true here? Because true and false, this is going to be false, right? Or true. But then, but if these two things were flipped in precedence, then we would get false here. So this is the situation where it's important to understand this, is that you can end up with like something where you absolutely cannot figure out what's going on, and you've got this issue and you don't know why it's wrong, and the reason that you don't know is that you're assuming that the precedence is something that it isn't. So we see a similar concept next called associativity. Associativity is which operation runs first when you have several of the same operation running together. So the example here might be in Python, 18 divided by 3 divided by 2. So this is going to come out one of two ways. We might get 18 divided by 3, which is equal to 6, divided by 2 equals 3, and that's what we see. Or we might get 18 divided by 1.5 if 3 divided by 2 were to run first, and then 18 divided by 3 were to run on the result of that, or 18 were divided by whatever the result of 3 divided by 2 is. So it's the difference between left to right associativity and right to left associativity. Python uses left to right associativity. Swift, it turns out, also uses left to right associativity. So it is the same in this circumstance. The point of this being that if you're running into like a strange situation with the result of something where you have multiple operators happening on the line, you may want to check your precedence and your associativity. All right, finally, let's talk about what these two languages compile to. So one thing to note here is that the language that another language compiles to is not a characteristic of the language itself. It is a characteristic of the compiler that you are using. So for example, there are compilers available that will compile Python to C, that will compile Python to Ruby. The most commonly used one compiles Python to C, but that's a characteristic of the compiler. We can compile it to whatever we want based on what the machine is that we're running on, what the specific purpose is that we're using the code for, these types of things. Similarly, folks have written compilers for Swift to all kinds of things. The version of Swift that we run on iOS compiles to LLVM. That's not an acronym, that's the full name of the project. It's called LLVM, and it was acquired by Apple and from a graduate student project, as a matter of fact, and has continued, Apple's continued to develop it in order to run Swift on iOS, macOS, tvOS devices. It's good to know what your programming language is compiling to give you a basic idea of some of what, like how the language is developed, what it might be getting developed for. It's also valuable if you end up needing to debug something and you want to go in and like disassemble the language and look at exactly what's going on there, which we won't end up hopefully having to do in this class, but knowing what it compiles to gives you some of that background that might be helpful for understanding some of the choices that were made when this programming language was written. And that's the final point that I want to make about these programming languages. We see that there are ways in which Python and Swift are the same. And we see that there are ways in which Python and Swift are different. The reason that that happens is that programming languages are built by people or groups of people who have different perspectives on what a programming language should look like and how it should operate. Some programming languages are for specific purposes, or people might just have different opinions about the way a programming language should work. And a programming language at its core is an expression of those values that a programmer had when they were writing it. It's valuable for us to know that that exists and to consider it when we're looking at a programming language, because it can help us understand, based on what other programmers were valuing, why the language or framework or app is written the way that it is. We will come back to this concept over and over in this class of understanding the reasons why something is written the way it is, the trade-offs that were associated with that decision, and how our world might be different if those decisions were made differently.